less than we wish. But maybe now that refrain from making comments about the world order and the sanity of our system. And just say we're grateful that you're here from EPFL and boson. And I'll let you take over. That's better.
Thank you very much, Venice. Yeah, it's always a pleasure to be here, really. So what I will talk about today is Weyl-invariant Einstein-Cartan gravity, unifying strong and hierarchy puzzles.
I think I have to push that. Okay.
It worked.
There's two
You have
okay things here. One of
You have to press it on the desktop, not on the laptop.
yeah. Oh, with this, what was confusing me? Ah, there we go. Sorry about that.
Okay, so the work I'm going to talk about is was done together with the Georgios Karananas and Sebastian Dell, both at LMU in Munich. So I will
It's yippee.
So I will start from meditating what is the best way to get gravity from particle physics. Then I will discuss an important symmetry which may be added to description of gravity, which is called Weyl symmetry. Then I will discuss Einstein-Cartan Weyl-invariant theory, and will show that that's an interesting theory, which may have something to say about strong CP problem, about Higgs mass, HNL masses of heavy neutral leptons, cosmological constant, and then I will discuss a rather theoretical issue concerning Euclidean continuation of this theory, which may be interesting. And finally, I'll come to conclusions.
Can it, in principle, even have cosmological predictions? Quantitative, I mean. If you tune your parameters, whatever, non-Gaussianity, something like this, or am I wasting my time?
Well, it can have inflation.
In principle.
In principle,
Okay.
yes. Yeah, also, so there will be axion that there might be either curvature fluctuations, etc. But this is work in progress. I'm not going to talk about that.
Right.
So you should decide by yourself whether you are wasting your time.
Okay.
Okay, so what is gravity? If there are several answers to this question. So if we stick to historical approach, then and follow Einstein, then we may say that gravity is not an ordinary force, but rather a property of space-time geometry. And if we want to describe evolution in gravity, then the theory which would govern that can be called geometric dynamics. And you can look at the famous book which describes this point of view. I mean, this is the way, in a sense, as we normally teach gravity. I mean, when I was teaching general relativity, that was the way I was teaching. You start from a principle of equivalence, and then you develop a geometrical viewpoint. And of course, there are many arguments in favor of this type of thinking. Okay? It's there is a solid experimental evidence and astronomical and human-sized distances. The theory is mathematically beautiful. If we accept this point of view, then the natural intention would be to try to construct some unified theory which unifies gravity with other interactions. And then the idea behind would be geometrizing all other forces in nature, like electrodynamics, etc., etc. Well, this ideology or this point of view is not unique. We can say, well, from particle physicist's point of view, gravity is nothing special at all. It's just electrodynamics. Okay, so in electrodynamics, we have a field which transmits all electrodynamic interactions, which is a massless particle, spin 1. Okay, in gravity, we have graviton instead of spin 1 particle. So it's like particle physics, but with a low energy limit containing spin 2 gravity. Okay, and then geometry. Then gravity is not geometric dynamics, it's simply a low energy limit of some more complicated theory. Okay, what we can say is success of this point of view. Well, the success coming from particle physics, where quantum mechanics and quantum field theory are doing very well in describing the observed world. We can even say, okay, there is a way how you get a photon and graviton. Okay, you can say that I would like to search for a theory in which we have a photon and massless photon and a massless 2-spin particle, and then you are automatically coming to electrodynamics and to general relativity. Okay, so it is the second approach which I'm going to take, and I will try to convince you that it has several benefits in comparison with the standard way of having the gravity theory. Okay, so let's try to see how we can get gravity. Okay. So if you talk about standard model, then a way to do so is the following. So you start from some global symmetry. For the case of electrodynamics, it will be U1 global invariance. And then what you do to get electrodynamics, to get photons, you say that, well, this theory should be local. Therefore, we should have a gauge field, which is associated with the symmetry. And this gauge field happens to be the photon. So if you now have the standard model, you can say, okay, let me have a global theory, which is a theory which is globally invariant with respect to SU3 cross SU2 cross U1 symmetry. Okay, no question why it is this symmetry which is used in nature. Okay, let's assume this is the case. But if you start from global symmetry of this type, then after we gauge this symmetry, we get the standard model. Okay, now we got the standard model, but there is still some global symmetry in the game. And this global symmetry is nothing but Lorentz symmetry and symmetry against translations, which are global. Okay, so we have yet Poincare group, which is global symmetry here. So why don't we consider the localizing this symmetry, gauging this group? And indeed, I mean, it was proposed quite a while ago by Uchiyama, Keeble, and Kiyama at the end of 50s, beginning of 60s, that if you do so, you will get theory of gravity. And aesthetically, that looks very appealing to me. Okay, there are no global symmetries at all. All global symmetries which you have should be gauged, and in this way we are getting all interactions, including gravity.
But you do assume some strange background, namely Minkowski. Is
Yeah,
it
yeah.
annoying?
Yeah.
From the point of view of normal gravity, it is very annoying, right? Because maybe we live on a sphere. Or
Yeah, but you say I construct my theory against Minkowski background. I gauge this symmetry. Then we are getting gravity, and we are getting all this curved space, etc., as a result of this generalization.
And background somehow disappears.
And background disappears. No background.
So you're saying I'm not losing non-trivial topologies at all.
No.
Okay.
No, the ground disappears, and after you are going through this procedure, and I will tell you how you go through this procedure, you get a theory which doesn't depend on initial Minkowski background, which is
Even on the topology of the initial background.
no.
Okay.
So you will get some dynamical theory. So how this
Even for regular gauge theories, you can expand around different background topologies, right? An instanton background, and you have
But the background will be remembered in the resulting theory, right? And
you have to
gravity.
sum over all backgrounds also. Yeah, you have to sum
But
over all.
but here, if I
No,
hear
but-
Misha correctly, background totally disappears. Even the topology of the background is lost. If I hear you correctly. But yeah, let's.
No, but say for instantons and stuff like that,
The background
you-
is remembered.
well, it's not remembered. These are the boundary conditions
Exactly.
which you impose.
Exactly. But I'm asking
for-
the same question about gravity.
no.
You are not imposing, so it is different in this
Uh-huh.
respect from you. That's why I asked, right? It's different. Okay.
Okay, so what are the objects? Well, actually, I think this is a beautiful construction which people invented. It actually goes back to Einstein-Cartan to Cartan geometry. It's also associated with different geometrical structures which you may or should use in describing a different curved space type. Okay, so the objects, mathematical objects, which are inside gravity as a gauge theory. So there are two of them. So the first one is tetrad 1/4. Okay, so everybody knows what tetrad is. Roughly speaking, tetrad is the square root of the metric if you use metric formulation of gravity. Or it's better to say you make a square of tetrad and then you get the metric. So this is a familiar object, and yet another one, it's called spin connection. Okay, and this object is nothing but the gauge field of the Lorentz gauge group. Okay. So Lorentz gauge group, as you know, it has 6 generators. And well, these fields are associated with the 6 generators of the Lorentz group. The indices A and B, they are associated perhaps with what Andrei was asking. So they are labeling the lat space-time indices. And the index mu here, which is a Greek letter, is associated with curved space coordinates. Okay. But yeah, and this guy is antisymmetric with respect to indices A and B, which gives you exactly 6 generators. Okay, so the and these objects are very natural from the polling point of view. You know that if you would like to describe fermions in curved space-time ground, you must have tetrad and you must have omega. So that's the way how Dirac equation is generalized to curved space-time. Okay. So it's kind of unnatural to have metric formulation of gravity, which doesn't have this geometrical object inside. And then what you gain out of that? Yeah, you can count the number of fields, 16 fields for tetrad and 24 fields for spin connection.
I'm sorry, and all those are an analog of A mu in electrodynamics.
Yes.
All these are primary fields.
All these are primary fields.
Okay.
Actually, this one tetrad is associated with translation, and so this guy is,
Well, translations and rotation. Okay. Yeah,
this guy
sure,
is
sure.
associated with the Lorentz transformation. Oh, that looks a little bit scary because you say, yeah, I have 16 fields here, 24 fields here. That makes us 40 degrees of freedom for gravity. And we know just graviton, what happens with other fields, but I will come to this question later. Okay, so there are different gauge covariant objects. So this is the analog of just F mu in electrodynamics, or corresponding construction for other gauge fields of the standard model. So you see here really a familiar structure for non-abelian field. So there are these pieces which are associated with the fact that Lorentz group is non-abelian, and actually this curvature, well, it's also called curvature for the gauge fields, right? It will happen to be connected with usual curvature, which we have in formulation of gravity. And then there is yet another object which appears here, which is called torsion. Okay, and this is again, yeah, it's basically you have a covariant derivative, as usually we have in the gauge field. This covariant derivative is constructed with the help of gauge field omega, and so here is yet another combination of different objects, which gives you a tensorial structure which transforms uniformly under different gauge transformations. Okay, so these are the mathematical structures which appear there. And now we can construct the theory using the similar rules as we have for construction of gauge theories of the standard model. Okay, so you ask yourself, what are the lowest order invariants which we can construct out of curvature, torsion, and other quantities. So one of the objects will be called F, will be related to curvature. And so you see this tensor, and then what you do, you contract this tensor with different stuff which is in your hands. Okay, so like a tetrad, you can use antisymmetric tensor. Yeah, then this is yet another structure which you can construct here. So what unifies these two structures is that they are related to the curvature, F mu, okay, and they have dimensionality GV squared. And the similar thing you can do with torsion. This is the torsion tensor. This is the guy with.
How come you get two scalar curvatures? Because of torsion or something?
Yeah, because
Okay.
of torsion.
Okay.
Well, Yeah.
Like a normal theory where I start from G mu nu, I don't get a torsion, and therefore I only get one curve.
Yeah,
Okay.
yeah, this is because in the normal metric gravity, which is based on Riemann geometry, the
But if I start with tetrads, I get this.
not necessarily. No, the issue here is not tetrad, or the issues here is
Gauging
the symmetry.
Poincaré,
Is the
right.
symmetry of Christoffel symbol.
Right.
So in if you say I have
So
Riemann,
sorry, Misha. So Einstein like overlooked this possibility.
no,
in some sense.
No, well, the good name for that is Einstein-Cartan gravity. So these two people developed it. So no, Einstein did know about.
So like
that.
it was already clear to
Yeah, it
Einstein
was-
that his theory is not the most general one.
Yes, yes, yes.
Okay.
So it's okay. Once you look at that from a geometrical point of view, what do? Okay, you say there are different geometrical objects, and they're constructed in the way how you do parallel transport of different vectors.
Okay, so this is more general connection. In
Yeah,
some
it's more
sense.
general connection.
Okay.
You can say, my connection is symmetric with respect to two lower indices, Christoffel symbol. Then you are coming to Riemann geometry and to standard gravity, which is taught at school. Now, once you say, no, my Christoffel symbols are not necessarily symmetric with respect to two lower indices, then you get another object, and this is exactly torsion.
Okay.
So this is the correspondence between
Clear.
these two things. I mean, so for instance, in Riemann geometry, you take a curvature tensor, right? And then a curvature tensor is symmetric if you change two pair of indices. So this is not necessarily the case once you
No,
have
I think I know this stuff, right? Thank you.
Okay, so what I'm now doing, I'm kind of using this notations, this notion for constructing a gauge theory of gravity as we would do in particle physics. We have torsion, well, three indices, too many. You can construct several irreducible objects. One of them you contract torsion in this way. You get some vector, which is called vector torsion, and this vector will be important in what follows. Then you can contract it with epsilon tensor. You get another vector, which is called axial torsion. And then there is some irreducible stuff with three indices where you subtract different traces. Okay, these are some details which will be mostly not essential in what follows. Then you say, okay, let's try to construct gravity along these lines. Okay, so what we would do in gauge theories, we would select lowest order dimensional operators. Right. So what are the lowest order dimensional operators? As I told you, this guy has dimensionality GeV square. This guy has dimensionality GeV square, and torsion vectors, they have dimensionality GeV to the first power. Okay. So the lowest order action in this sense, we just write lowest order dimensional operators is just written here. So F and F tilde is our curvature invariance, and then you write here all possible combinations which are invariant with respect to all these symmetries, which are constructed from the torsion vector and torsion tensor. Okay, so you may think that, okay, there are 40 degrees of freedom, but in fact, this action, it contains just 2 dynamical degrees of freedom. And then you can do this computation in your head without basically doing anything. So here you see that these guys, they are not dynamical because there are no time derivatives. You find equations of motion which say that all this torsion stuff is equal to 0. Okay? So no torsion. And
Sorry, that's a choice of the sort of physical system or?
no, I mean, once you said I would like to have lowest order Lagrangian and I'm not including further terms, then that's it. Okay, it's like
Are you saying v squared is 0 identically?
yeah, v is 0. No, you find the equation of motion. All these variables are independent. So, for instance, you're interested what is v. So you make a variation with respect
Oh, it's
to v.
independent of all other terms.
Yeah.
Okay.
And then you find that all torsion terms are equal to 0. And so in and then you can look more precisely in the form of this f and f tilde, and then you find that all these variables are gone except gravity. Okay. So this is a complicated way of deriving Einstein theory, if you will.
So is the graviton some linear combination? What is it?
No, the graviton would be associated with the with tetrad. Okay, so the letter G mu is kind of square of A. Well, you can pronounce different words. I don't. I'm not sure we can really put inside some physical meaning in this term, but you can say, okay, G mu is a square of tetrad. So the graviton is a bound state of this tetrad. This is perhaps nonsense complete, but mathematically, you start from a theory which has well, several gauge fields, and then at the end of the day, you get just propagating gravity.
But in principle, it's the same like ABU. Originally, there are 4 of them, but you get 2 degrees of freedom. It's the same,
It's
just more complicated
it's
version.
more complicated version of that. Okay, so the short conclusion from this story, if we are talking about pure gravity, then the Einstein metric formulation is not unique one. You can consider other ideas. For the lowest order theory, they lead to one and the same action. Okay, so you don't bring anything new to your theory from a dynamical point of view. Okay, so now I kind of switching the topic for a short time, and we'll discuss yet another symmetry, which was introduced more or less at time of Einstein, which is a Weyl symmetry. Okay, a short historical reminder. If you want to geometrize everything, you want to geometrize electromagnetism as well. And Weyl proposed that this can be done if there is not, if the theory is not just invariant with respect to all diffeomorphisms, but it also is invariant with respect to change the length of the vectors. So this is Weyl symmetry. Weyl symmetry, it didn't work that time because it was realized very quickly that the electrodynamics associated with Weyl symmetry just gives you everything wrong about electrodynamics. But this this symmetry is very interesting from itself, also from particle physics point of view. Because if you have a theory which is Weyl-invariant gravity, and then if you limit your consideration to flat space-time, then you find out that your theory is invariant with respect to conformal symmetry. And so what is conformal symmetry? Conformal symmetry is a symmetry of Poincare transformations, and then there are several extra transformations. One of them is scale invariance, okay, where you rescale the length of your vectors. And yet another one is associated with special conformal transformation. So basically, conformal symmetry, it's a transformation of coordinates which doesn't change the angles between two lines. That's an interesting symmetry. If you look at three Maxwell equations and ask yourself what is the symmetry of that, it's not just Poincare, it's Maxwell equations are invariant with respect to conformal transformations. So conformal symmetry, it has 15 generators, 10 Poincare plus another 5. If you look at the standard model, just write Lagrangian of the standard model and put the Higgs mass to 0, you will find out that this Lagrangian is not just Poincare invariant, it's conformally invariant. Okay, which is interesting. And the conformal field theories are interesting if you have exact conformal invariance that fixes different Green's functions. For you, 3-point Green's function can be expressed, can be found in some exact way, 2-point functions as well. If you look at different critical points where you have second order phase transition, then in many cases, the theory around this point is conformally invariant. Conformal field theories describe limiting behavior of different quantum field theories in UV and infrared. And also, as they don't have infinities. It's a finite theory that looks good. No need renormalization, nothing. And as I said, if you take Lagrangian of the standard model, then it is conformal invariance if the mass of the Higgs field is equal to 0. I'm talking about classical Lagrangian. And that's interesting. This means that the symmetry is enhanced when the mass of the Higgs boson is put to 0. Yet another interesting point is that the energy of the ground state of conformal field theories are equal to 0. Okay, we know that cosmological constant is very small, so maybe there is a relationship. So these are just hints. I mean, nobody was really able to construct a theory which uses all these facts to explain everything. Okay, but maybe these are interesting coincidences, but if these are coincidences, they're interesting. Okay, so now what I want to do, I want to say, okay, suppose that we have this interesting construction, Einstein-Cartan, in which Poincare group, to be more precise, Lorentz group is local. Suppose that we add to that requirement of Weyl symmetry, getting even more symmetric theory. And let's see what can be the consequences of these theories. Are they interesting? Maybe they don't make sense.
And now you no longer insist that your Lagrangian be quadratic.
Yeah. I'm coming to that.
Okay.
That's exactly the point. So how do we implement the Weyl symmetry? It happens that the implementation of Weyl symmetry for Einstein-Cartan construction is very natural and also very interesting. Once you have the gauge field, like in electrodynamics, so once you have local symmetry, then you have the gauge field associated with this local symmetry. And once you look at different transformation laws of different geometric quantities in Einstein-Cartan gravity, you will discover that there is a field associated with torsion, which transforms as an abelian gauge field. Okay, so this is the transformation, Weyl transformation. So Weyl transformation, what it does, it simply rescale the tetrad or the metric if you use the metric formulation of gravity. It doesn't touch the gauge field associated with Lorentz group, well, different component of torsion transform in a different way, but there is the vector torsion, which transforms exactly as a U1 gauge field associated with the Weyl transformations. Okay, and this is a very big difference between Einstein-Cartan formulation gravity and metric formulation of gravity. If you try to use metric formulation of gravity, and if you try to construct quantum field theory which respects Weyl symmetry, then you fail, because there is a famous Weyl anomaly there. And this is not the case here for Einstein gravity, exactly because of the presence of this gauge field, which transforms non-trivially with respect to Weyl transformation. Okay, so now let's try to construct the action which would correspond to Einstein-Cartan Weyl-invariant gravity. Okay. As I said, Weyl transformations, so scale transformations are also a part of Weyl transformation. And any theory which is scale invariant must not contain dimensional full parameters, because if you have any dimensional full parameters, that is going to break the scale symmetry and Weyl symmetry simultaneously. Therefore, the action which I was writing, which contained the Planck mass, is not admissible. Okay, so we have to do something else, and it should be an action which doesn't contain any dimensional full parameters, and therefore this action should contain different squares of different curvature invariant. Okay, so now if you say, okay, I would like to write the most general action, which is Weyl invariant, so then this action will contain many of these square invariants, but then you will be in trouble, because then many degrees of freedom which were unphysical, that could have been removed from Lagrangian, are now dynamical. And they're not only dynamical, they happen to be ghosts. So why they happen to be ghosts? It's easy to understand, because the Lorentz group is not compact. And once you make a square of different type of field strength, then there are minus signs appearing in many places. And then you find out that the theory is unstable. This is still an interesting theory. It was studied by many people from the point of view of renormalizability. Okay, so Kelly-Stelle showed that variants of this theory, they contain ghosts, but they are renormalizable. Okay, so this is interesting. It's not clear how to deal with the ghost. So let me take the most conservative point of view, saying that I want to write just the action which is Weyl invariant and doesn't contain ghosts at any choice of parameters. Okay? And this is the section. So you have f squared, which I introduced, it was curvature. Then you have f tilde, which was some combination, a little bit different combination of f mu and tetrad and epsilon symbol, or you can have the cross term between the two. Okay, so this action for basically any choice of parameters, it doesn't contain ghosts, as we will see in a second. And what we will see in a second, that this Lagrangian just contains graviton and the scalar degrees of freedom, nothing else. So how do you see that? Let me remove for simplicity the cross term. It can be added, but it doesn't change anything. And let me do the following. Okay, so this is our action. we have f square. So here I put little f, and then this little f may be understood as a gauge coupling of the Lorentz group.
Who invented this thing?
Sorry?
Who invented this Weyl-invariant Einstein-Cartan?
Well, invented.
Who wrote this Lagrange?
We.
Oh, really? So people did not try it before?
I don't think people tried before this Lagrange. No.
And it's compatible with GR?
Yes, as we will see in a second.
Okay.
Yeah. We will see in a second that it's not only compatible with GR, but it's better than GR. Okay. So, well, people did consider R-square gravity, which is also very interesting theory.
But
So-
the R squared probably is not good enough, right?
No, it's excellent theory as well.
Oh, really? So R squared does not contradict observations?
No. You will see, because
Okay.
there are. I'm not going to talk about R square gravity, but some discussion which I'm.
Because naively, it looks like R squared is very different from R. How come it describes the same
Yeah,
GR?
it's the same here,
Okay,
right?
you will
But
explain.
You will see, I will explain how it works. Well, what kind of is interesting to me is that once you're writing that, then you are limiting a lot the freedom. Well, limiting the freedom is not a good thing, but I think in field theory it's a good thing. Okay, so you have less parameters to play with. So how do you do with this theory? It's convenient to make a relationship with the usual metric formulation of gravity, since we all know how to handle that. And so this F guy, it can be rewritten through usual normal. Yes.
Sorry, you may have mentioned this and I've missed it. In principle, you can also write Higgs square F term in the Lagrangian. Is that something you're going to talk
No,
about?
Higgs square times F square you cannot write, because that will break Weyl-invariance. But what you can write is Higgs square times F.
Yeah, that's what I meant.
Yeah, and I will come to that.
Okay.
Yeah. So at the moment, I'm talking about just pure gravity without adding any matter fields, and I will add matter fields later on. Okay, so these are helpful formulas. They show how this curvature tensor in Einstein-Cartan gravity is related to normal Riemann curvature R and different components of torsion. So this is what happens with F, and this is what is F tilde. So you see F tilde, it doesn't contain any geometry associated with curvature, but it contains a lot of stuff associated with torsion. Okay, so how do you solve this theory? So this theory is solved in the following way, and R square theory can be solved in the similar fashion. Okay. So what you do, you introduce auxiliary field, two of them, because we have two structures, F and F tilde. Okay, so I have here high square and here high to the fourth, and here I have F tilde, phi to the first power, and here phi squared. Why it's fourth and second power, it basically doesn't matter, it's just convenience of notations. And so what is the trick? Once you have this, once you introduce these auxiliary fields, you see that the equations of motion for high and for phi tell you that high is proportional to F and phi is proportional to F tilde. You insert it back and then you get the action back. There is even a special name for this type of trick, which people use in condensed matter theory, which I always forget, and it's associated with the name of some condensed matter physicist who invented it. Okay. Now, how do you see that this is a good theory? You see it in the following way. You have Weyl-invariance, and since you have Weyl-invariance, you can make a Weyl transformation which removes one of the scalar fields. So, for instance, we can remove the scalar field which is high here. I just say that high is equal to m Planck square root of 2. And then we see that the original Lagrangian is equivalent to that. Okay.
I'm a little confused here. Where did the Planck mass get into that? I thought we were scaling.
It's any number. It can be any number, any dimensional full number. High is the scalar field with dimensionality 1, and so it's just any number.
But you put M Planck because you want to reduce it to normal Einstein
Yes,
field. Right?
that's correct. So we can put any number, but then once we analyze this Lagrangian, we will see that this is nothing but the Planck scale.
But you didn't let the Higgs have a mass or anything.
Yes, exactly. And that I'm coming to.
So why not?
Yeah. That's what we will. I'm waiting to that.
But I think I have the same confusion. You want the Lagrangian to have Weyl invariance, but yet you introduce dimensionful scaling here. Doesn't that break?
No. This is it doesn't break exactly in the way as the Higgs vacuum expectation value doesn't break SU2 symmetry.
But it gets to the expectation value because you had a mass parameter in the theory to begin with. So, but here you didn't.
No, here it's just a gauge choice. Right? You have gauge invariance and gauge. I mean, in the standard model, you have gauge invariance. You can go to unitary gauge if you want. You still have gauge invariance, right? But it's hidden. It's one-to-one correspondence with that. Here we have gauge invariance, meaning that we can change our variables in the help of conformal Weyl transformation, and we just make this transformation in such a way that one of the fields, it can be whatever. But here I just chosen this field high to be a constant. Okay. So after that, we have this type of theory. Okay, and all torsion components are non-dynamical as well, but you have one more degree of freedom, which is field phi, which tells you that the dynamical content of this theory is graviton plus some scalar field, nothing else. Now we can look at the particle spectrum of this theory, and then you find that this gauge coupling F, it determines vacuum energy. So from the point of view Einstein-Cartan Weyl-invariant gravity, cosmological constant is nothing but the gauge coupling. Okay. Another gauge coupling determines the mass of this scalar. Okay. Now, if you say, well, these are gauge couplings, and I find that this is interesting interpretation of this term, that the gauge coupling determines the cosmological constant, for instance. And cosmological constant is very small, so the corresponding gauge coupling should be extremely small. So perhaps this is manifestation of this conjecture that the gravity is the weakest force of nature. So here, the force of gravity is associated with these gauge couplings, and these gauge couplings are required to be small. Okay, so now that was a pure gravity. Okay, and pure gravity is the same as at the Einstein field. Plus extra.
Except for the extra scalar.
Except for the extra
Okay.
scale. And you can solve exactly in the same way the R squared gravity in the metric formulas, and you will get you will come to roughly the same conclusion. So R squared gravity without any other terms, pure, is nothing but
Except for some fifth force, which you can make arbitrarily small or something.
yeah, if you want, yeah. Okay, so now we want to add a standard model. There are fermions which we want to add. Well, there are certain rules how you produce covariant derivatives here. So they're used here. The covariant derivatives of fermion contains this gauge field, and then there are some other terms which will be important in what follows, which are admitted by Weyl-invariance, which give you the interaction between vector and axial current with the axial torsion field. Okay, and then if we have the scalar, then the scalar comes with non-minimal couplings to F. So these are also the terms which are admitted by Weyl-invariance. You have H squared times F, H squared times tilde, and different connection to torsion. And so now you can write the whole Lagrangian and study for its properties. Okay, so what may be a relationship to strong CP problem? So we have our new field, and this is the only new field in this theory, which I will call A. And then this field, it has some mass, okay, which comes through the gauge coupling, but it also has an interaction with axial and vector current. Okay, now if the gravity-induced mass, yeah, and since this field has this type of interactions, and moreover, these interactions are nonlinear with respect to this field, then this field also is getting mass from QCD, and it does the same thing as the axion, provided the mass induced by gravitational interactions is smaller than this is the mass induced by gravitational interaction, is smaller than the mass induced by the QCD effects. Then from physics point of view, it's undistinguishable from the Pache-Queen axiom. And this is the constraint on these couplings. Okay, so these guys zeta are couplings associated with axial and vector current. This is F tilde. So if this coupling is very, very, very small, then this is the particle which can solve strong CP problem. So I find it kind of appealing because of the following reason. If you stick with the solutions to the strong CP problem, which is associated with Pache-Queen symmetry, then this Pache-Queen symmetry is introduced in a way by hands. It is introduced in order to solve strong CP problem. Okay, and moreover, if you take QCD without axion, you have to tune initial theta angle. It should be 10 to the minus 10. So this is without axion. But if you have axion, then in popular models, you are actually introducing many new degrees of freedom, 6 degrees of freedom in KS/Z, idea S/Z. And in order for this to work, you have two natural numbers. One of them is the ratio of electroweak and page Green scale, which is 10 to the minus 14. And also you have to require that the page Green symmetry is not broken by other effects, which tells you that the breaking of page Green symmetry scale divided by this scale should be of the order of 10 to the minus 15. Okay, whereas here the origin of this particle is associated with gravity. There's no page symmetry; it's explicitly broken there, but it's broken by gravitational effects. So we can take the complete theory, and in addition to axion, then there is Higgs. Okay, the mass of the Higgs are also proportional to M Planck, but it's proportional to this gauge coupling constant. Okay, so taken at the face value, this immediately contradicts to experiment. Why so? Because you say, aha, this F is we fix F by requiring that cosmological constant is small, so F is extremely small number, and therefore the prediction is that the mass of the Higgs is extremely small. Okay? So I consider this actually as a strength of this theory because of the following reason. There are different corrections to these quantities. So as we discussed, there is non-trivial, non-perturbative correction coming from QCD for the axion mass, okay, which makes it much larger than the gravity-induced mass. And here, for the Higgs, there could be different non-perturbative corrections, which can bring this mass to some more civilized value. And actually, quite a while ago, we considered different sorts of non-perturbative corrections associated with scale of gravitational instantons, and we saw that this type of scenario may be possible. Though it's not conclusive in the sense that one cannot do really first principle computation, computing everything there. Okay, and yet another benefit I will talk about shortly is, okay, we all know that the standard model is not complete. Perhaps the simplest and the minimal fix for the standard model is associated with adding 3 right-handed neutrinos to the theory. If these 3 right-handed neutrinos are added, then you can get all neutrino masses and be in accordance with neutrino physics. You can generate baryogenesis symmetry of the universe. You can have dark matter candidate. Okay, so in the theory which I was just discussing, the mass of these guys is just equal to 0 in 3 approximation. Okay. Why it's equal to 0? Because no term which is Weyl-invariant, no mass term which is Weyl-invariant is admitted to these particles. Okay, and that's interesting. Why? Because the mass of these guys breaks lepton number. Okay? And we do expect that once we have a gravity theory, that all global symmetries are broken by gravitational effects. And therefore, it's natural to expect that some mass will be generated for these particles. Okay, and if this is a non-perturbative generation, then they may happen to be small and thus achievable by searches of different experiments. Though this is wishful thinking at the moment, and I can't show any convincing computation how this mass is generated, and if it is generated, how big it could be. Okay, and just to finish, I just want to discuss a little bit more theoretical part here, which is associated with continuation to Euclidean space-time. Okay, so what is the trouble here? If you have an Einstein theory of gravity, and if you try to make it to do non-perturbative computations on the lattice or whatever, then you cannot do so. You cannot do so because the corresponding action, Einstein action, is not positive definite when you make a rotation into Euclidean spacetime. Okay. And then you get all crazy things associated with that. It's interesting that potentially Einstein-Cartan gravity, it allows you to do so. Yeah, the reason is simple, because you have here squares, and when you make a analytic continuation of this theory in Euclidean space-time, then for certain signs of these parameters and f and f tilde, you get an action which is bounded from below. Okay, and I'm coming to the end. So I think that Weyl-invariant Einstein-Cartan gravity is an interesting theory. So it has just one extra degree of freedom, axion-like particle, in comparison with the standard model. All the parameters which appear in this theory and which are of our concern, such as the axion mass, the Higgs mass, and cosmological constant, they all happen to be at the tree level. They all happen to be related with the gauge coupling of the Lorentz group. Okay? And if these gauge couplings are very small, then the tree values of these parameters are very small, and that opens a potential possibility of computation of this parameter with the use of nonperturbative physics. I just said about Euclidean action and about H&L masses, and of course there are many open ends here. Part of them are more complicated, part of them are relatively easy. So there is a question: what happens in cosmology? Can we get inflation in the theory? Can we get Higgs inflation? What is the behavior of axion-like particle? Do we get, for instance, either curvature perturbation? Can this type of axion-like particle be a dark matter? So that's what we are looking at now. And of course, from theoretical point of view, this theory is not renormalizable by standard methods. Okay, so the question is how to deal with perturbation theory, and this model at high energy is how to compute non-perturbative effects. These are all open questions. Thank you very much.
What is the value of the total potential energy of this system in its ground state and state? Is it negative, large, small, positive?
No, it's proportional to the gauge coupling constant. So it's not fixed. It's m Planck to the fourth power times square of the gauge coupling. So that's and so you cannot say what it is. I mean, you can say, okay, I can compare it with cosmological constant today, and from here you get the extremely small number for the gauge coupling. So there are certainly free parameters in this theory. So
And Higgs self-coupling, what happens to Higgs self-coupling, like you know what the mass of the Higgs is?
Yeah.
What is the,
No, here it's a free parameter.
just free parameter?
Yeah, Higgs coupling is a free parameter. But there could be different ideas about what this free this free parameter can be. One of them is associated with, say, asymptotic safety. Then you can fix it. You get the correct value of the Higgs mass in this case.
Okay with the rest of the.